So suppose you had a function, as presented, and you were trying to figure out what value of x would have this function return 3 as an answer. So this is exactly backwards to what your BEDMAS stuff is. Instead of being given the input and asked to find the output, here I've been handed the output and asked what values would cause that to occur. So algebra really is just order of operations backwards. So if we were to follow those same 3 rules that we had before, which were 1, evaluate the arguments, 2, execute function, and 3, external stuff, we just have to undo all these steps. And if we can undo them in the correct order, then we'll have returned the input that gave us 3 as the output. So the first thing you have to do is imagine that there is an answer. So let's start with that. Let's start with x. With x. Okay. Now, if you started with that x there, if I knew what it was, so let's say it's 10, the next thing you do according to order of operations is once you had that x, you would add 4, which would give you x plus 4, whatever that number is plus 4. The next thing you'd had to do would be multiply by 2, which would give you 2x plus 4. At that point, you would have finished evaluating the argument, so it would be time to execute the function. So execute square root. Wow, that's not even close to the word execute. Execute square root. Should have given you this. Once you'd executed the square root, we start applying the external stuff, which means you would have had to multiply by 3, giving you this. And then finally, you would have subtracted 12, which would have given you this full thing, which we've recently been told is worth 3. Okay. So, if you can take a minute to appreciate what's happened, if I know what the input is, order of operations gives me a list of things to do in order to crank out an output. So if I have the output instead, I just have to go back through these steps and undo each of them. So if I were to do that, instead of starting with x, if I started with this number, what I want f of x to equal, and I start undoing these steps. Take 3 and undo subtracting 12. Well, if you undo subtracting 12, that's addition. So 3 plus 12 would give me 15. Okay. Now that I have this step done, I have to undo this one. Undoing multiplication requires division. So I'm going to have to take my answer from the last step and divide it by 3, which gives me 5. So that step is done. Now I have to undo an execution of square root. So this is the only step that is different for different functions. You're going to have to remember how you undo a square root. And of course, in this example, it's squaring. I'm going to make a little note there. What you did there was you summoned the antifunction. So square root and square are a special pairing because they undo each other. So when you get to this level, or the step in the problem, when you have to undo the radical, you need to summon its antifunction pairs, which is squaring. If this thing had been square, then you would pull square root here. If this was cube, you would use cubed root. If this is cubed root, this would be cubed. So every function has a way of undoing some other function. So you're going to need to make a list of those things. We're going to go through, we're going to finish this radical example. So you'll see that the antifunction for a radical is squaring. We're going to do a ln, so you can see its antifunction. We're going to do an e to the x, and we're going to do a rational expression so that you'll get all those antifunctions written down. Anyway, 25, or 5 squared is 25. Now I have to undo this multiplication by 2, which requires me to divide by 2, which is 12 and a half. I have to undo adding 4, so 12 and a half subtract 4 gives me 8.5. And that's it. That's the input that should render an answer of 3. Now, you probably haven't seen it done this way before. So I'm going to erase it in a minute, and we'll run through it the way you've normally seen this done. But I want to check this number first. So let's run it through these steps. 8.5 plus 4 would be 12 and a half. 12 and a half times 2 would be 25. The square root of 25 is 5. 5 times 3 is 15, and 15 subtract 12 is 3. So by reversing these steps, you were able to reverse engineer the input from the output you receive from that function. And that's the entire point of algebra, is to be able to work backwards through the steps in order to figure out what number went in to have this number come out. So if I clean this off for you, and then we will try this in the more traditional fashion, leaving 8.5 up there. What you've probably seen before is you take the function and you set it equal to that number. You pull this over to the other side. If it's a negative on this side, it's adding on that side. So 3 plus 12 equals 3. 2x plus 4. 3 and 12 is 15. That's a familiar number. That crept up in the way I had it done before. Okay, divide both sides by 3, gives you 5. In order to break a square, you have to square root both sides because you are summoning the antifunction. Square 5, you get 25. Don't forget your brackets. Divide both sides by 2, gives you 12.5. And bring the 4 over, gives you 12.5 minus 4 is 8.5, which is, of course, the answer we already had. So one of these two methods works for you. This either makes sense to you or it doesn't. The other method, where you wrote out the list of steps and then systematically undid them, maybe that works for you. It doesn't matter which one you choose. You just need to be able to have some sort of framework that you can walk through in order to help you undo steps for each algebra thing. So I'm going to clean this off, and we're going to try a logarithm. Okay, so I'm going to go through and I'm going to write the list of steps out first, so the first way. And then I will leave you to try and figure out how to make the more traditional method work. So if I start with this x here, according to the order of operations, I have to evaluate this argument first. So if I start with x, the very first thing I'm going to have to do is subtract 3. Once I've subtracted 3, I have to do this to it. Now, that says take a quarter of this answer. So you can either think of that as multiplying by a quarter or dividing it into 4 pieces, whichever you prefer. I'm going to use divide by 4. Once you've subtracted 3 and then divided that by 4, you're supposed to apply the ln. So execute ln. once you've executed the ln, you're to multiply by 5. And once you've multiplied by 5, you're to add 1. And allegedly, if you do that, you should get 11 as your answer, because that's what it's asking you to solve. So I'm going to go through this list of steps, and I'm going to try and figure out what x value would generate 11 as my output. So if I go backwards, 11, reverse this step would be 10. 10, reverse this step would be 2. 2, this is the line where I need to summon the anti-function for ln. So you're going to have to remember what function undoes ln. So if you can note this down, ln of whatever is the anti-function of e to the whatever. So in order to break a ln, I'm going to have to take e and raise it to that exponent. And e squared, I'm going to have to grab my calculator to do that, gives me 7.389. I have to undo this step now, which would be 4 times 7.389, which gives me 29.556. And then I will have to undo this step, which would be 29.556 plus 3, which gives me 32.556. So there you go. If I input 32.556 into this function, it should spit out 11 as my answer. And the neat thing about these questions is, now that you know that, all you have to do is feed this thing back into the function and make sure you get 11, right? The whole thing is self-checking, so there's no way that you can get anything less than 100% on this particular unit. So let's give it a try. 32.556. So I'm going to start with that number here. Subtract 3 gives me 29.556. Divide by 4 gives me 7.389. Take the ln of that answer, and I get 1.999992408. Now that's probably supposed to be 2, but I'm just going to leave it there approximately. Multiply by 5, and then add 1, gives me 10.99996. Now that's awfully close to 11. Because I had to use the e, I had to round at some point, so I'm not going to get exactly 11, but I got awfully close. So within a rounding error, this number does spit out that output. So you should probably make a note somewhere that these two functions are anti-function pairs, and then remember it for the next one. Okay, so this one is an exponential base e, so I'm going to have to remember what the antifunction for e to the x is. But I can still write out these steps for my x. So if I had that x there, the first thing I'm supposed to do is evaluate the argument. So I would have to take the x, and from the x I would have to subtract 4, and then I would have to divide it in 2 because of that 1/2. Then I would have to execute e to the x. Once I'd executed e to the x, I would have to divide by 3. And once I've divided by 3, I have to subtract 5. And allegedly, that will give me 6 as my answer. Okay, so going back up through these steps, undoing them. Undoing subtract 5, I would have to add 5, which would give me 11. Taking that answer, undoing divide by 3, you accomplish that by multiplying by 3, that gives me 33. We're going to have to figure out how to undo e to the x. So So I have to apply its anti-function, and I'll have to remember from the last example that e to the something is undone by ln to the something. So in order to undo e to the x, I will have to ln the answer I get. So I summoned my anti-function, and I will have to put that into a calculator. Ln of 33 gives me 3.4965, which I'm going to round to 3.497. Take 3.497 and undo this step, so that means I have to double it. Gives me 6.8, 6.994. 6.993. And then my 6.993, undo this step, gives me 10.993. So allegedly, if I feed 10.993 into this function, I will get 6 as my answer. So you can't make a bold claim like that without actually going to check it. So starting here with my 10.993, going to subtract 4, gives me 6.993, divided by 2, gives me 3.4965, execute e to the x, so e to that exponent gives me 32.9997, which I bet is supposed to be 33. It's close. Divide by 3, gives me 10.9999, which I bet is supposed to be 11. It's close, but not quite. Subtract 5, gives me 5.9999, which is pretty close to 6. So I've confirmed that this input does in fact give me 6 as my output. So here's one of those weird fractiony looking ones. So I'm going to switch it to negative exponent notation so you can see which parts of the argument and which parts are not. So the 3, the x, and the negative 8 are all in the denominator. So they are all in the argument of this particular function. And we're going to try and find when this function is worth negative 2. So we're going to solve that. All right, so list of steps. You start with the x. The first thing you do is subtract the 8. Once you subtract the 8, you multiply by 3. Once that's done, you need to execute the rational expression, execute whatever to the negative 1. Once that's done, you multiply by 4, and once that's done, you add 2. And allegedly, that's going to give us negative 2 as an answer. Okay, so we just have to walk back through those steps. Negative 2 plus 2, negative 2 subtract 2 if I undo that one. Gives me negative 4. Negative 4, undo this step would be divide by 4, which gives you negative 1. Bring this up here. I have to summon the anti-function for something to the negative 1. Okay? This function's a bit weird. The anti-function for something to the negative 1 is something to the negative 1. It's its own anti-function. So in order to undo this, I'm going to have to apply it to the other side. Negative 1 to the negative 1 is 1 over negative 1, which is negative 1 is my answer. Bring it up here. Negative 1, undo this, divide by 3, gives me negative 1/3. Bring that up here. Negative 1/3 plus 8. Well, 8 is 24/3, which gives me 23/3 as my answer. Lovely. Now, to check it, we could run through this with all the fraction rules if you like, but I don't want to do that. We're just checking anyway. So I'm going to approximate that as 23 divided by 3 is 7.667. So I'm going to run this through these sequences of steps and see if I get -2 as an answer. So 7.667 subtract 8 gives me -0.333. Times 3 gives me -1. That thing to the exponent -1 is -1. Times 4 is -4. Plus 2 is -2. So it works. So you've got this process then for how to get through solving any function you like. As long as you can write the steps out where you evaluate the argument first, then execute the function, then apply the external stuff, and then systematically undo all those steps in the correct order. So far we've used some antifunction and function pairs, and I'm just going to write them down so that you can see which pairs go together. So if your function is x squared, the thing you need to break that is plus or minus square root. Now that's a bit of a weird one because you need the plus or minus on that. If you have a radical, you break that with squaring. Notice that the plus or minus is not necessary on this particular step. If you have e to the x, that is broken with ln x, and vice versa. E to the whatever. If you have 1 over x, that is broken with 1 over whatever. This one is hard to write down. So let's use the negative exponent notation. X to the -1 is whatever to the -1, and vice versa, obviously, because those are the same thing. So far I have 1, 2, 3, 4, 5, 6, 7 functions. Right, 1, 2, 3, 4, 5. 5 of my base functions, so that leaves 2 left, the sine and the cos. Now you should have been working on the sine and the cos in the independent study and realize that the antifunction for sine is this thing, and the antifunction for cos is this thing, and this is named arc sine and this is named arc cos. So when you come across these functions in your steps and you're trying to undo them, there's your list of antifunctions in order to get it done. So off to the practice problems. Good luck.